A child goes sledding down an icy hill before reaching level ground 15 meters below. They slide into an area of grass which has a coefficient of friction of 0.20. How far do they slide before coming to a stop? Right, so as soon as you see friction in a problem, or if you have like a person pushing or pulling on something, you know that you're going to have to include external work in that problem. So let me draw a little sketch of the problem here. So, okay, that's a very extreme sledding hill, but that's okay. And we can add in our grass. It's probably brown and dead because it's wintertime if you're going sledding. So, and then we have the child in the sled, starts, comes to a rest somewhere down here. You know, they start basically from rest, so they didn't get like a running start. So they just kind of edge out over the hill to get going that way. So we want to know what's this distance, right? How far did they travel through the grass? So we can label that here to here, and I'll call that distance D. How far did they travel through the grass? Oh, and the other thing that we need to, so we'll define our height equal to 0 at the bottom. So that means that we're starting at a height of 15 meters at the top. Let's look at our points, right? So we're going to connect point 1 here to point 2 there. I'll take my system to be the child and Earth system here. So that means that I'm going to use a potential energy due to gravity in my calculation. So let's go ahead and write down our energies at point 1 and point 2. The types of energy that we can have here. So in this problem, there aren't any springs. So the only types of the only types of energy that we have possible are going to be potential energy due to gravity and kinetic energy. That the child just starts from rest and just, you know, sort of gently eases out onto the descent. So the kinetic energy to start is going to be 0. So the energy at point 1 is going to be just the potential energy due to gravity. So that's mgh. So you'll notice, okay, we have the height given, but we don't have the mass of the child given. So we're expecting, you know, if this is a well-written problem, we're expecting that that mass is going to eventually cancel out. Okay, how about the energy at point 2? Right, so potential energy due to gravity, and then plus kinetic energy. Well, let's look at the problem statement. It says that they are coming to a stop. So that means that the kinetic energy is 0. And they're at the bottom of the hill. So the potential energy due to gravity there is 0. So that means that our energy at point 2 is just 0. So here we can see right away that there must be some external work. And as I said, and whenever you see friction, you know there's going to be external work. We know, and we can also tell that because this is not 0. The energy 1 is not 0, but energy 2 is 0. Right, so they're not always the same. So that we do our next step, which is to say, okay, the external work is going to be equal to the change in total energy, which is equal to E2 minus E1. Well, our external work here is going to be the work done by friction. So I'll go ahead and just write work done by friction is equal to E2, which is 0, minus E1, which is mgh. Now we need to remember what the definition of work is. In this area here where the where friction is doing work on the sled, the displacement is toward the right, but the force of friction is toward the left, right? So we know that the work done by friction is always negative because the force of friction always points opposite to the direction of the displacement. So I can say that the work done is going to be negative of the force of friction times the displacement, and that's going to be equal to negative mgh. Right, so now I have a negative on both sides, so I can cancel that out just so I don't have to keep copying that down. The force of friction is equal to mu, the coefficient of friction, times the normal force. Right, and in this problem, if we could draw a quick free body diagram, we're going to have normal force pointing up, the force of gravity, you can write mg, pointing down, and then the force of friction pointing left. Right, so there is an unbalanced force, right, which is going to cause an acceleration, slowing us down. But what I'm really looking at here is in the vertical direction, we have the normal force and the force of gravity are the only things in the vertical direction, so we know they have to balance out. So, if you want to be thorough, you should write down, well, F net in the vertical direction is normal force minus gravity. There's no acceleration in that direction, so they equal 0. Or we can just we've done this enough that we can hopefully cut to the chase and say that the normal force here just balances out the force of gravity, so it's going to be equal to mg. Right, so I can take that and which gives me mu mg is the force of friction. One thing to note here is we can't actually calculate a value for the force of friction, right? Because we know mu, we know g, but we don't know the mass. So we have to do this one algebraically. So we have to bring that over here and say, okay, force of friction is equal to mu mg times and then we have the displacement there. So that's going to be the work done by friction, and that's equal to mgh. Right, so that's just copying down this equation here, but replacing the force of friction with mu times mg, canceling out the minus signs because there's a minus sign on both sides. Okay, so now we see what we hoped and what I knew would happen is that the mass cancels out. So I'll just cross that out on both sides. And then we're trying to find the displacement, how far the child is able to sled through the grass. So I'm trying to solve for d, so that means I should divide by mu times g on both sides. I've got g times h divided by mu times g. If you didn't notice, I mean, that's fine because we know what g is. So if you had just plugged in numbers, you'd be fine. But that's going to save us some calculation. So that's going to give us h divided by mu. Okay, so our height was 15 meters. And mu is a number, 0.20. So dividing by 0.2 is like multiplying by 5. So that would give me 75 meters. In this problem, we had a situation, the energy was not conserved, right? So there was external work done by friction. And so whatever energy that we had to start, that was all taken away by friction.